Now let us discuss the concept of vapor pressure and cavitation. First of all, let us try to understand what is the vapor pressure. Right. In thermodynamics also we will introduce this term, what is the vapor pressure. Here also we can see what does we mean by the vapor pressure. If we can say that all the liquids will have a tendency to evaporate when it comes in contact with a gaseous atmosphere. Right. If you put a glass of water, open the glass of water in this room, then the liquid or that water will have a tendency to evaporate, and that evaporation is also depend upon the temperature of this room, the humidity condition of this air, and all so many things are there which we will discuss in thermodynamics and refrigeration and air conditioning both. Let us discuss that. The vapor pressure, if we can say that all the liquids will have a tendency to evaporate when they are exposed to this gaseous atmosphere, right? And this rate of this evaporation will depend. This rate of evaporation will depend upon the molecular energy of this liquid, how much the energy of this liquid will have, how much the energy these molecules of this liquid will possess, and which is totally depend upon the temperature, right? So we can say that this rate of evaporation will totally depending upon the temperature. So for the bullet points, if I write here that all the liquids will have a tendency to evaporate, right? And this rate of evaporation is a function of temperature. It depends upon the temperature. And the vapor molecules, these vapor molecules which evaporate, these vapor molecules will exert a partial pressure on this liquid surface, and that partial pressure is known as vapor pressure, right? So these vapor molecules exert a partial pressure on liquid, and this partial pressure is known as vapor pressure. This is known as vapor pressure, right? We will elaborate it. I'll elaborate it also. So we can say that, let us suppose we have this container. This space is confined. We have this closed container. Let us say we have this closed container. Just for the understanding, I'm making this. We have this container, and in this container we have, let us say, this water. This is closed one. We have water, right? We have water, and some temperature is there outside. Some temperature is there, and we have here, let us say, air. Right. We can say that if this is the case, and if the space is confined, and this beaker or this water is maintained at a constant pressure, at a constant temperature, then this water will have a tendency to evaporate. Right. This water will have a tendency to evaporate, and these water vapors will come on this space. Right. In this space, the water vapor will start depositing. So this is the evaporation. After some time, there is the condition that these vapor molecules will be forced to condensate. Right. After some time, we can say that an equilibrium condition will evolve. After some time, equilibrium condition will be there when the vapors will be forced to condensate, and on this equilibrium condition, if equilibrium condition is maintained, we can say that the rate of evaporation will be equal to the rate of condensation. So this is the equilibrium condition. When this equilibrium condition will achieve, the space above the liquid surface will become saturated. When this equilibrium condition will achieve, then this space will become saturated, right? The vapors which this space can take is there, right? So this air is now saturated, or this space is now saturated. So we can say that the space above the liquid will become saturated with the vapor, right? The vapor pressure, now these vapors will exert a pressure on this liquid surface. These vapor will exert a pressure, and it will depend, and this is known as the vapor pressure. Right. And we can say that the vapor pressure of this given liquid, this saturation level, and this vapor pressure of this given liquid is a function of temperature only. It is a function of temperature only, and this is equal to the saturation pressure for, we can write here, just for your understanding, that now these molecules, these saturated vapor will exert a pressure on this water, and this is known as vapor pressure, and the vapor pressure of a liquid is a function of temperature. It is a function of temperature, and it is equal to the saturation pressure for, please make it clear, for boiling corresponding to that temperature. This is the vapor pressure, right? So we can say that the vapor pressure will be equal to the saturation pressure for boiling corresponding to that temperature. Let us say we have 100 degrees Celsius or 50 degrees Celsius temperature. Corresponding to that 50 degrees Celsius temperature, we can say what is the corresponding pressure for boiling. That is known as your vapor pressure. We already discussed in the thermodynamics that we can boil a liquid by two ways. You can boil a liquid by two ways, either by increasing the temperature to the boiling temperature, or by making the pressure of that liquid to the vapor pressure, right? So we can say that the saturation pressure corresponding to this temperature of this air or this surrounding is the vapor pressure of this liquid, right? So we can say that, hence we can say that vapor pressure will increase with temperature. As the temperature is increasing, vapor pressure is increasing, right? As this temperature of the surrounding is increasing. Start. Now let us discuss the concept of vapor pressure and cavitation. First of all, let us try to understand what is the vapor pressure, right? In thermodynamics also we will introduce this term, what is the vapor pressure. Here also we can see what does we mean by the vapor pressure. If we can say that all the liquids will have a tendency to evaporate when it comes in contact with a gaseous atmosphere, right? If you put a glass of water, open the glass of water in this room, then the liquid or that water will have a tendency to evaporate, and that evaporation is also depend upon the temperature of this room, the humidity condition of this air, and all so many things are there which we will discuss in thermodynamics and refrigeration and air conditioning both. Let us discuss that. The vapor pressure, if we can say that all the liquids will have a tendency to evaporate when they are exposed to this gaseous atmosphere, right? And this rate of this evaporation will depend. This rate of evaporation will depend upon the molecular energy of this liquid, how much the energy of this liquid will have, how much the energy these molecules of this liquid will possess, and which is totally depend upon the temperature, right? So we can say that this evaporation, this rate of evaporation will totally depending upon the temperature. So for the bullet points, if I write here that all the liquids increasing, the vapor pressure is increasing, so it is a function of temperature also. And we can say that the phenomena of boiling of liquid, the boiling of liquid, you can make it, or you can relate the boiling with the vapor pressure. You can relate the boiling with the vapor pressure like that. The boiling will start when the pressure will become equal to the vapor pressure. When the pressure of the liquid will become equal to the vapor pressure, then the boiling of that liquid will start. So we can say that the boiling can be achieved by two ways. Either you can raise the temperature. Suppose for this water, you know that water will boil at 100 degrees Celsius at 1 atmosphere, right? So at 1 atmosphere, if you make the temperature to 100 degrees Celsius, then this will boil, this water will start boiling. So we can say that at 100 degrees Celsius for water, the saturation pressure is 1 bar. The saturation pressure is 1 bar. What is the saturation pressure? The pressure at which water will start boiling, it is 1 bar. So 1 bar is now the vapor pressure at 100 degrees Celsius, right? And if we want to say we want to boil the water at 50 degrees Celsius, then the saturation pressure for 50 degrees Celsius, we can say that the saturation pressure will be 0.5 bar, let us say. So either you can change, either see there are two ways to boil a liquid. Either make the temperature constant, or you change the pressure, or you make the pressure constant and change the temperature. If the temperature will corresponding to the saturation temperature, then water will start boiling. If the pressure will become equal to the saturation pressure at that temperature, then the water will start boiling. Right? There are two ways. If you remember the TS diagram, if I show here, okay, we go one step ahead, right? No issues. Right? Let us say if I can write TS diagram here, this is the dome, and if I show the constant pressure lines, these are the constant pressure lines. These are the constant pressure lines. Right. Let us say this is pressure P2 and this is pressure P1. Right. We can say, let us say this is temperature T1 and this corresponding temperature is T2. So we can say that at temperature T1, there are so many pressure lines. It's at temperature T1, the saturation pressure is P1. Right. So at temperature T1, the vapor pressure is P1. Right. So if you want to boil any liquid at temperature T1, you have to take the vapor pressure P1. Similarly, for the temperature T2, the vapor pressure will be T2. This is the saturation pressure corresponding this T2. Right. So you can boil like this, and we can say if the pressure is constant, then you can boil with the help of increasing or decreasing the temperature. So this is the concept of vapor pressure. So we can say that when a liquid or when any, let us say, water is flowing through any tube or any pipe, if the water is flowing, right, we can say if the water is flowing, and in the process, in this flow process, the pressure of the flow, pressure inside the flow will become less than the vapor pressure at that temperature. What I mean to say is, let us say this is a pipe. Just to understand, make you understand, I am saying that let us say this is a pipe in which water is flowing, and outside temperature is, let us say, 50 degrees Celsius. And corresponding to 50 degrees Celsius, let us say that saturation pressure will be, or vapor pressure will be 0.5 bar. 0.5 bar. During the flow, something happens, something happens, and I can say that at this section, when this water will come at this section, here, the pressure will go to 0.4 bar. If during the flow, the pressure will be less than or equal to vapor pressure, corresponding to this temperature. If you change the temperature, vapor pressure will change, right? Vapor pressure. Then if at this point, if this is the case, then the liquid will start converting into vapor. Now here, this water will start converting into vapor. Right. If the pressure will be less than or equal to the vapor pressure, then liquid will start converting into vapor. Now, from here, this vapor will start flowing. These liquid vapors will start flowing. And when this liquid vapor comes to high pressure area, high pressure region, you can say, right? The pressure inside it will be 0.4 bar, right? When, let us say, at this section, the pressure is, let us say, 2 bar. During the flow, here the pressure is 2 bar. When these liquid vapor will come here, this water vapor will come here the pressure is more. When they comes to the high pressure region, because of this force, because here the force will be more. Inside pressure is less, outside pressure is more, then vapor will burst. In this case, vapor will burst. And if the vapor will burst, then we can say that at high pressure area, the vapor will burst, and if this bursting of vapor will be near to this surface, let us say here, near to this surface, this pipe surface, and if this vapor will burst, then from all the direction water will come. Inside we have air. So when it bursts, then from all the direction water particles will come with a very high velocity. With the very high velocity water will come, then it will create a wave. And this wave will cause the erosion. This high frequency wave will cause the erosion of this tube or of this pipe. And this phenomena is known as cavitation. So cavitation is the process in which is the phenomena when during the flow, if you make the pressure less than the vapor pressure, then vapor will start flowing, and when these vapor will come to increasing, the vapor pressure is increasing. So it is a function of temperature also. And we can say that the phenomena of boiling of liquid, the high pressure area, they will burst, and if they burst, then from all the sides liquid will come and a wave will generate, and this liquid will come and a wave will generate, and this wave will make the erosion of this tube or of this container, and this is known as cavitation. So when we will discuss the turbine and pumps in the hydraulic machines or fluid machines, our main focus in the fluid mechanics or fluid machines will be only one thing, that during the flow, any liquid will flow, the pressure will not be less than the vapor pressure in any case. In any case, the pressure will not be less than the vapor pressure corresponding to that temperature. If vapor pressure will reach, then cavitation will occur, the vapor will form and they will burst at the high pressure area and they will cause the cavitation. So you have to be more careful that when you design any fluid problem or when you solve any fluid problem, then there should not be any chance that you make the pressure less than the vapor pressure. And based on this, we will discuss what is the net positive suction head in case of pump, right? Why we use the draft tube in case of your turbines, what we are using in case of turbine to avoid this cavitation, and where the cavitation is maximum, and so on. We will discuss it later on. This is the concept of vapor pressure and cavitation. Stop. Start. Hello friends. In this session, we will discuss about the next chapter of our fluid mechanics, that is pressure measurement, or we can say manometry. Right. So this is the basic chapter of your fluid mechanics, and we will discuss it in detail. And believe us that after studying this pressure measurement from this lecture, you will be able to solve all the numericals based on your manometry. If you want to calculate the pressure in any manometer or differential manometer, you will easily solve it. Right. So first of all, let us discuss about what is a pressure. We know that pressure is a normal force per unit area. Right. Pressure is a normal force per unit area, and the pressure is always a compressive in nature. We know that pressure is always a compressive in nature. So if I write, the formula of pressure will be equal to force per unit area. This force is the external force. Don't confuse it with the stress. Stress is the internal resisting force per unit area, but this force is the external thrust or external force. So if we say about what is the unit will be Newton per meter square, and you know that 1 Newton per meter square is known as 1 Pascals. So this is the SI unit of pressure, 1 Pascal or 1 Newton per meter square. So we say that if the fluid is at rest, what do we mean by that? What is the meaning of fluid is at rest? So if the fluid is at rest means that there should not be any relative motion between the adjacent layers. The adjacent layers of the fluid, in between the adjacent layers of the fluid, there should not be any relative motion. Then only we can say that fluid is at rest. So we say that if the fluid is in a stationary container, right? If the container is stationary, or if that fluid is flowing with constant velocity or constant acceleration, then we can say that fluid is at rest, right? So if the fluid is at rest, we know that if the fluid is at rest, in this case, there should not be any shear stress. Shear stress will be 0, and only normal compressive force is acting. Only normal compressive force is acting. We already discussed it. Only normal compressive force is acting, and that normal compressive force is a pressure, right? So we say that for a fluid, when the fluid is at rest, so in that case, the Mohr circle is a point on x-axis. Right, we already discussed it in strength of material. Just for your revision sake of point, I am writing here that if the fluid is at rest, in that case, Mohr circle is a point on x-axis, or you can say on sigma axis, right? On sigma axis. Why it is a point? Because we know that at a point, the pressure in all the directions, the intensity of pressure will be same. We will discuss it later also, that this is known as your Pascal's law, that at a point, when the fluid is at rest, then at a point, the intensity of pressure in all the direction will be equal. That's why, in this case, the Mohr circle is a point on x-axis, right? So this is the basic definition of pressure. Pressure is force per unit area. Now we have different types of pressure. In the fluid, we will come across with the different types of pressure. That is atmospheric pressure, absolute pressure, gauge pressure, and last one is your vacuum gauge pressure. Right? These are the 4 different types of pressure which we are having. So now let us discuss one by one. First of all, let us discuss what is the atmospheric pressure. So the atmospheric pressure is the pressure exerted by, if I write here, it is pressure exerted by environmental mass. Right? The environment which is present, that environment is exerting one pressure on everything, right? If we talk about this marker, then this environment is exerting a pressure on this marker. That pressure is known as atmospheric pressure, right? Next one is your absolute pressure. Absolute pressure is the known as, we say that the real pressure of the system, or you can say net pressure of the system. Net total pressure of the system is known as absolute pressure, right? Total pressure of the system is known as absolute pressure, and gauge pressure is known as, if we talk about the gauge pressure, then the gauge pressure is defined as the pressure of the system. It is defined as the pressure of the system. Stop. Hello? Start. So the gauge pressure is pressure of the system. If we say that it is defined as the pressure of the system above atmospheric pressure. Above atmospheric pressure. It is defined as the pressure of the system which is above the atmospheric pressure. Means if we measure the pressure with the reference to the atmospheric, then it is known as gauge pressure. And if we measure the pressure with respect to the datum line is that line where the pressure is 0. If we measure the pressure from the datum line, then it is known as absolute pressure. And if we measure the pressure with reference to atmospheric, right? If we say that at present atmospheric pressure is 1 bar, and if we can say that if in of a system, if the absolute pressure is 5 bar, then the gauge pressure is 4 bar, right? Because if we measure from the 1 bar, it is 4 bar. So we can say this is the gauge pressure. And vacuum gauge pressure is, if we want to define what is the vacuum gauge pressure, it is the pressure of the system. It is the pressure of system below atmospheric pressure. Below atmospheric pressure. It is the pressure of the system below atmospheric pressure, right? If we define it with the help of a diagram, let us say that we'll define it for your better understanding with the help of a line diagram. If I'm saying, let us say this is the datum line. Let us say that this is the datum line or reference line. We can say if this at this the pressure is 0. On this datum line the pressure is 0, and we have this line. This line is corresponding to, okay, we'll make this. We have this line corresponds to atmospheric pressure. This line corresponds to atmospheric pressure. That means this distance is atmospheric pressure, right? If we measure the pressure of atmospheric from the reference or datum line, this is the atmospheric pressure. Now let us say that, suppose we have some pressure at here. Let us say this is point A, right? This is point A. Here the pressure is some pressure is there which is higher than atmospheric. Now, if I measure the pressure of this point A, from datum line, it is pressure absolute pressure of point A, right? But if I measure the pressure of this point A with reference to or from the atmospheric, if I measure this from the atmospheric with reference to this, so this is known as gauge pressure of point A. This is known as gauge pressure of point A. So this is the difference between absolute and gauge pressure. If you measure the pressure of any point from the datum line, it is known as absolute pressure, and if you measure the pressure from the atmospheric as a reference, it is known as gauge pressure, right? So from here you can write, you know that the absolute pressure of point A is equal to atmospheric pressure plus gauge pressure. So if I write here that the absolute pressure of point A is equal to atmospheric pressure plus gauge pressure of point A, right? This equation you will get from this. And in the fluid mechanics, we only deal with the gauge pressure, right? So it's better to understand here what do we mean by gauge pressure and absolute pressure, because atmospheric pressure is everywhere. In every fluid machines or any flow, atmospheric pressure will be there. We are more concerned about the pressure above the atmospheric or below the atmospheric, right? So we will take the atmospheric pressure as a reference and we'll measure the pressure from that point only. So in the fluid mechanics, we only dealing with the gauge pressure. You must remember this. Suppose you have some point here. Let us say you have some point B here, right? Some point B you have. So if I measure the pressure of this point B from the datum line, then it will be same absolute pressure of point B. But if I measure its pressure from the atmospheric pressure, if I measure it with the help of atmospheric as a reference, then this pressure is less than the atmospheric. This is atmospheric pressure and this pressure is less than the atmospheric. So this is known as vacuum gauge pressure. Of point B. So this is the meaning of vacuum gauge pressure. The pressure below the atmospheric, if we measure the pressure from atmospheric, then this is the vacuum gauge pressure. So from here you can write that atmospheric pressure will be equal to absolute pressure of point B plus vacuum gauge pressure of point B. Also from here you can write that vacuum gauge pressure of point B is equal to atmospheric minus absolute pressure of point B. And we write here like pressure of system below the atmospheric, it means gauge pressure is less than the atmospheric. So this is the equation you get from this. So this is the meaning of absolute pressure, gauge pressure, atmospheric pressure and vacuum gauge pressure. So you have to remember this, and if you understand it, then whenever we solve the numerical, if I say that it is a gauge pressure, then just keep in mind that that pressure is measured with reference to the atmospheric, not with the datum line. Stop. Start. Now let us discuss the hydrostatic law in the chapter your fuel pressure measurement. So hydrostatic law states that, let us highlight the important concepts. First one is pressure at any point in a fluid which is at rest is obtained by this hydrostatic law. I am reading the definition and highlighting the important points which you have to remember. That pressure at any point in a fluid which is at rest is obtained by this hydrostatic law, which states that the rate of increase of pressure in the vertically downward direction. That when you go vertically downward means in a vertical direction if you are going downward, right? In a vertically downward direction must be equal to the specific rate of the fluid at that point. If you want to find the pressure at any point in a fluid which is at rest, then it is obtained by this hydrostatic law, and it is saying this states that the pressure at the rate of increase of pressure in the vertically downward direction will be equal to the specific rate of this fluid at that point, right? So this is the meaning of the hydrostatic law. Now let us derive the equation for it. Suppose you have this container in which this fluid is there of density rho, right? This is a free surface, right? In fluid mechanics, we show the free surface by the symbol. Free surface means on this surface, the pressure is the atmospheric pressure. You just remember these things, right? Because in question, when it comes to gate or engineering surfaces, they may confuse you by not giving the free surface or by giving any other pressure on the interface or on this layer. So this is your free surface. I will show you. This is the free surface. So free surface means the pressure at this layer, pressure at this top layer will be atmospheric pressure, right? Now let us say that we take a point A here, we take some small element A, which is at a height h from the free surface. Just be attentive and listen all the words which I am saying. This element A is at a height of h from the free surface. So if I write here that h is the height of element, or you can say point A from free surface. So that means that you have to take the height, all the height from free surface. And we want to find what is the pressure here, right? So to understand it, I just make this A figure here in a zoom manner so that you will be able to understand the concept. So this is the element A. This is the small element A. This is the small element A, right? If I say this is the element A, which is, let us suppose this is the free surface. Let us suppose this is the free surface, right? So we say that this element A, this is element A, is at a height of h from the free surface. This is a very small element, and this depth of this is, let us say, dh. This is a small element, and this height of this small element is, let us say, dh. Let us say dh, right? And the area of this cross section, let us say, is A. Let us say A is the area of cross section. So if I write here that A is the cross sectional area of element, right? A is the cross sectional area of element. Now, if we talk about this top surface, we have some fluid here which will exert a pressure, on this top surface. Let us say that pressure is P. So on this top surface, a pressure, we know that it is always a compressive force, so the direction will be in the downward direction. A pressure P is acting, and you will take the area dA. Okay, dA you can take the area because it is a small element. We will take the area dA, right? So the pressure is P, so the force will be pressure into area, P into dA. And let us say that we know that as from the hydrostatic law, we know that as we go down in the fluid, the pressure will increase. Let us say on this bottom surface, we have a pressure in this direction because it is a compressive force. So the pressure will be in this direction. Let us say here the pressure is P plus dP. We assume that at this surface pressure is more. Let us say P plus dP, and the force will be P plus dP into dA. Force will be P plus dP into dA. Another force which is acting here will be the weight of this column. Right? Here we have this column. So weight of this column is also acting. Let us say this is the weight of this column is acting in the downward direction. You must be worried that, sir, why you are not taking the pressure force on this plane, this front and this back plane. So for your understanding, let me explain one thing. This is a fluid element. Here we have some pressure in this direction. Here we have pressure in this direction. If we talk about this surface, at each and every height, we have different pressure in this direction. On this surface, at each and every point, we have pressure force in this direction. So at the same height, this force will cancel out with this force, right? Because this pressure will be equal to this pressure at the same height. Okay. And if we talk about this surface also, at each and every point we have pressure in this direction, compressive nature. Here also we have pressure in this direction, compressive nature. So at each height, at each and every point, the pressure will, or the force will cancel out. Right? That's why we are not taking the pressure or the force on these four faces, because they will cancel out each other. But this top and bottom force will not cancel each other because there is a difference of height. Right? There is a difference of height here. So if we say that, if in this case, if I say for equilibrium,